In this example problem, we're returning to the cat that's prowling around the neighborhood. Except in this case, we're given just a little bit more information about the cat's motion. So we have if the cat in the previous problem takes 45 minutes to complete the first displacement, that is, it takes the cat 45 minutes to travel the length of vector A, and 17 minutes to complete the second displacement. So it takes an additional 17 minutes for the cat to prowl the length of vector B. What is the magnitude and direction of its average velocity? Now you got to be a little careful here because we're looking for the average velocity, not the magnitude and direction of the displacement. So many of you may be tempted to just solve for vector r, the magnitude of r, but that would be incorrect because this would be a displacement vector. We want to know what the average velocity is during this 62-minute period of time. So as soon as you see these two words, you should immediately write down your average velocity equation, which is VAV equals XF minus XI divided by TF minus TI. Now, this was the equation the way that we presented it before we covered vectors and unit vectors. But at this point, you should know that the velocity is a vector, so I'm going to put a hat over the V. And we also know that XF and XI are position vectors, so both of these also get hats above them. The time, on the other hand, is a scalar quantity, so neither one of these get a hat. But at this point, you may notice that it could get somewhat confusing because these are position vectors. So the XF hat and the XI hat are position vectors. They're a lot like saying A hat or B hat, whereas just X hat is a unit vector. So to avoid confusion between these two, you're going to see me writing the average velocity equation like this for the remainder of the year. So V average is equal to RF. So I'm just going to replace this variable XF with RF, just to avoid confusion with the unit vector X hat. So these are vectors, so they get hats above them, then RI divided by TF minus TI. So now we need to use this equation to solve for the average velocity of this cat during the entire 62-minute period of time. Now you may be tempted to use this equation to figure out what the average velocity is as the cat prowls the length of vector A, and then use this same equation to figure out what the average velocity is of the cat whenever it travels the length of vector B. But that makes the problem a little bit more complicated, and really you wouldn't get the correct answer in the end if you did it that way. So what we have to do is we have to use the total displacement vector here. So this is where the cat ends up. So really this vector R is my final R. So this is RF, and I've already rewritten it on the next slide. So RF is our magnitude R, which we solved for in the previous problem. So that leaves the question, what's RI in this case? So RI is where the cat begins. So the cat begins at the origin. So I can write my initial position vector as RI is equal to 0. Actually, let's leave out the parentheses. 0 x hat plus 0 y hat. So it's essentially 0. If you were to figure out what the magnitude of this was, it would be 0. And plus negative 72 minus 0 is just negative 72, and 120 minus 0 is just going to be 120. So for this particular problem, we can just say that the Ri is 0 and just cross it out. Now we know what the time is. The total time that it takes the cat to go from the origin up to the tip of point or vector B is 62 minutes. So my final time, my TF, will be 62 minutes, which means that my initial time is when the cat starts to move, which is just going to be 0. So TI is just 0 minutes. So we can also just cross that out of our equation, and we end up getting V average is just equal to RF divided by TF, the scalar TF. Now, plugging this in, we get V average is equal to RF, which is negative 72. So I'm going to leave this in component form. Negative 72 m x hat plus 120 meters y hat, all divided by the scalar TF, which is 62 minutes. Now, just following our math rules, we can, since both of these terms are being divided by the same time, we can divide that up into two different terms to get V average is equal to negative 72 meters divided by 62 minutes, and then x hat plus 120 meters divided by 62 minutes, and that's in the y hat direction. Okay, so now just plugging these into my calculator, what I find is that my V average in unit vector notation is approximately negative 1.161 meters per minute. That's in the x hat direction, so I haven't rounded yet. The only reason that I write the number like this is just that way we remember what it is, but I have not rounded this yet. I just can't write out the entire number, or else I won't have enough space to perform the calculations. Then plus 1.935 meters per minute in the y hat direction. So to find the magnitude of the average velocity, I just have to use Pythagorean's theorem. So I just got to do x squared plus y squared, and then take the square root of that. So we'll do that on the next page. So my magnitude of the average velocity is equal to the square root of negative 1.161 meters per minute squared plus 1.935 meters per minute squared. Make sure my square root is over all of that, which, typing that into my calculator, I get approximately 2.257 meters per minute. Now, following my sig fig rules, give me a value of, so sig fig rules give me a value 2.3 meters per minute. Now, it is customary to report your final answers in meters per second, so just in case you converted your answer to meters per second, that would be, so 2.257 meters per minute. Okay, now in 1 minute, there are 60 seconds. So you can see that my minutes would cancel out, and I would get a final answer of 0.0376. That's meters per second. And then following the sig fig rules, that would give me, so sig fig, that would give me a final answer of 0.038 meters per second. So both of these are acceptable final answers. So here's your final answer for the magnitude of the average velocity in meters per second, or this is the magnitude of the final average velocity in meters per minute. But we're not done yet. We still have to figure out what the direction is of this average velocity. So what I always do whenever I'm solving for the directions, I always plot the vectors x and y components on a coordinate system, which I have on the next slide. So we've got our x component is in the negative x direction. So this is my v average x component there. So it's the negative 1.161 meters per minute. So I'm going to write v average, and then comma x for the x component. And then we have the y component is positive 1.935 in the y direction. So again, I'm not drawing these to scale because we're using the analytical method, so we don't have to. So this is my v average in the y. Now, if I want to, if I wanted to solve for the magnitude, I need to take this vector, take the tail of this vector, and move it to the tip of the other one. So I move it up here. Try to draw the same size the best that I can. So that's also my v average in the x, and then my final magnitude for the velocity will be from the origin all the way up to the tip of v average in the x direction. So that's my v average magnitude there. Okay, so the angle that I'm going to solve for first is going to be this angle from the positive y-axis. So to solve for that, I'm just going to use tangent. So tangent of theta is equal to the opposite, so the x component. So the v average, comma x, divided by the adjacent, which is the v average, comma y. So the v average, comma y. So all that says is just the y component of the velocity average and the x component of the velocity average. So we do tangent of theta is equal to the x component, which is negative 1.161. But remember, I never plug these negatives into my trig functions just because I think when you start getting negative degrees and when you're measuring from so many different axes, it can get somewhat confusing. So I always plug in positive values into my trig functions. So positive 1.161. So 1.161 divided by the y component, which is positive 1.935, 1.935, and both of these are meters per minute. That one's meters per minute, but the units cancel out in both cases. So I just get tangent of theta is equal to 1.161 divided by 1.935. Taking the inverse of both sides, I can solve for theta, which is inverse tan of 1.161 divided by 1.935. And that gives me an angle of approximately 30.96 degrees, but that is measured from the positive y-axis. The angle that I want to report for my final vector is counterclockwise from the positive x. So the final step is to do theta final. Okay, so I'll do theta final is equal to 90 degrees. Okay, because that is the angle between the positive x-axis and the positive y, and we'll add the 30.96 degrees to get a final answer of 121 degrees from the positive x-axis, and that is to the correct number of significant figures. So what we have here is the average velocity magnitude is 2.3 meters per minute, or 0.038 meters per second, with an angle that's equal to 121 degrees from the positive x-axis. Okay, I hope that helped. If you have any questions, just raise your hand and ask.